So today I'm here with lecture 6, right? Lecture 6. So today first I'm going to discuss energy of capacitor, right? Potential energy of capacitor, right? Potential energy of capacitor or energy stored in capacitor, right? Energy stored in capacitor. Energy stored in capacitor, right? So to find the energy of capacitor, we have to calculate work done, right? Okay, so work done, to find the energy we have to calculate work done, right? Work done by external, right? Now I'm going to draw three figure. Okay, so you have to understand. Suppose this is plate of your parallel plate capacitor, right? Okay, see, this is initial condition, right? This is initial condition. Initial condition, there is no charge on capacitor, right? Initially there is no charge in the capacitor, right? So this is initial condition, right? Initial condition. Okay. This is intermediate. Intermediate condition, and this is your final condition, right? Okay, now what is intermediate condition? Basically what external agent is doing, right? External agent is doing work, right? How they doing work? They bringing charge from this plate to this plate. Suppose this is your plate 1, right? And this is your plate 2, right? So he is bringing charge from plate 1 to plate 2, right? How much charge they bring? Very small charge, dq charge they bring, right? So they bring dq charge from this plate to this plate, right? Okay. So this is your plate 2, this is plate 1. They are bringing charge from plate 1 to plate 2, right? Plate 2 to plate 1, right? How much charge? dq charge, right? So you can see here they are bringing positive charge on this plate, right? So after some times positive charge will come on this plate, right? Okay. Suppose after some times he is bringing dq amount, right? Every time he is bringing like that, okay? So after some times charge on positive plate will become how much? Plus q, right? And minus plate 2 it becomes minus q, right? He is doing these things all the time, right? Now what happened? dq amount of charge is going to this one, right? Okay. So at final condition, right? At final condition, this one is this plus plate 1 got charge plus q, and this one got minus q, right? This is your intermediate state, right? But this is your final condition, right? So how much work he did to bring amount charge q on this plate, right? That's what we are going to find, and that will be your energy of capacitor, energy stored in a capacitor, right? Okay. So first I'm going to calculate a small work done, right? I'm going to calculate a small work done bringing a small charge on this one, right? Okay. So after that I'm writing here, okay? So here we can write let external agent transferring charge dq from plate 1 to plate external agent transferring charge dq from plate 1 to plate 2, right? Okay, yeah, 2 to 1, plate 1 to 2, right? Let external agent transferring charge dq from plate 2 to plate 1, okay? 2 to plate 1, okay? At any intermediate state, intermediate state, at any intermediate state, charge on plate 1, charge on plate 1, charge on plate 1 becomes plus q, and charge on plate 2, becomes minus q, right? Now a small work done by external in transferring dq amount of charge dw, right? dw, and this dw is v into dq. Okay, you know work done is equal to v into q, right? So v into q, what is the value of v? Okay, so yesterday you tried one formula, q is equal to cv, right? So v is equal to what formula? q by c. So v is q by c. So this type charge on capacitor is how much? Q. So we can write q, in place of v we can write q by c, right? So q by c into dq. Okay, no doubt up to this everything is clear to you, right? Okay, so this is a small work done, right? And we have to find total work done in bringing charge q, right? So by integrating this one we are able to get total work done, right? Okay, so I hope you written all these things, right? So let external agent transferring charge dq from plate 1 to plate 2 at any intermediate state, charge on plate 1 becomes this much, right? And charge on plate 2 becomes this much, right? So a small work done by external in transferring dq amount of charge dw is how much? This much, right? Now total work done we have to calculate. So integrating this value we are going to find total work done, right? And total work done will be your energy of capacitor, right? So I hope you written this one. So now I'm going to have this point. Okay, so now total work done by external in bringing charge q from plate 1 to plate 2, right? And suppose that work done is w, right? And that w will be total work done by external in bringing charge from plate 1 to plate 2. Okay, so plate 2 to 1. Okay, plate 2 to 1 dw is integration of this one, right? And lower limit is 0 and upper limit is becomes q, right? Because initial charge of the capacitor was 0 and final charge becomes q. So lower limit is 0 and upper limit is q. We have the value of dq, right? And we have the value of dw, and dw is how much? q by c, right? Into dq, 0 to q. Okay, so further we can write c 1 by c. C is a constant, right? It will come out. Okay, and now integration of this one. So you have what value? dq, 0 to q, dq. Okay, and this integration is how much? 1 by 2 c. Right? So further we can write 1 by 2 q square by c. So this is your formula to calculate work done, right? So work done we calculated, right? And this work done will be the energy stored in capacitor, right? So further we can write energy stored in capacitor, u. Suppose u is energy stored in the capacitor, right? And that u will be equal to w, right? So So that is equal to W, and W is how much? Half Q square by C. So this is your formula to calculate potential energy or energy stored in a capacitor, right? Okay, so you can see here, if charge on capacitor is Q, so potential energy will be half 1 by 2 Q square by C, right? Okay, so now I'm going to, we are also able to write this formula in another form, right? Okay, so how I'm going to write? So just see that one. Okay, now you can see U is equal to half Q square by C. You know this formula, just try to write now, right? But this Q is equal to how much? CV. This Q is CV. So another form of this formula is also possible, right? So those things we are going to find. So 1 by 2 and Q is equal to how much? CV square divided by C. So 1 by 2 C square B square divided by C. This cancels. So C, what value is coming? Half CV square, right? What value is coming? So U is equal to half CV square. This is another formula to calculate energy stored in a capacitor, right? The potential is given and capacitance is given. With the help of this formula, you are able to calculate, right? Another formula is also possible, right? Again, see from here, what is the U is equal to half Q square by C. Another formula we are going to derive, right? So see, we can write like this or not. This is your Q by C. We can write like this or not. No doubt. We are able to write like this. Q into Q. This is becomes Q by C. And Q by C is what? B. Q by C is B. So we can write here 1 by 2. Q by C is B. B into Q. So another new formula for calculate energy storage, Q into V. Half Q into V. So these are the three formula which is useful to calculate energy stored in a capacitor, right? In different situations you are going to use different formula, okay? I hope everything is clear to you, right? So next I am going to discuss combination of capacitor, right? So basically two types of combination of capacitor is given in your books, right? So many combination is possible, mixed combination and all those things, right? But those things are not given in NCERT, okay? So those things I'm not going to discuss. I will discuss only parallel capacitor and here I will discuss only series combination and parallel combination, right? Okay, so combination of capacitor, right? So basically two types of combination is possible, right? One is series combination, right? And another is parallel combination, okay? So suppose capacitor is connected like this. This is one capacitor, right? Is connected by another capacitor like this, right? If capacitor is connected like this combination is known as series combination, right? Suppose this is your capacitance 1, C1, this is your capacitance 2, this is your capacitance 3, right? Okay. So this type of combination is known as series combination, right? So what is the equivalent capacitor, right? So in class 10 you have studied, right, equivalent resistance, right? So this is, so in that class there was combination of resistor, right? But this time we are going to discuss combination of capacitor, right? So equivalent capacitance of these three. What is the formula for equivalent? Suppose C equivalent is equivalent capacitor of these three, right? And that equivalent will be how much? 1 by C1 plus 1 by C2 plus 1 by C3. So this is formula to calculate equivalent capacitor of a series combination, right? Okay. So similarly we can write for parallel also. So if capacitor is connected like this, okay? So this is your C1, this is your C2, this is your C3, right? If capacitor is connected like this combination is known as parallel combination, right? And for parallel combination formula is what? C equivalent is equal to C1 plus C2 plus C3, right? Okay. So as you see, this is just opposite of resistor, right? In class 10, right? For resistor, this kind of formula is useful for parallel combination, right? But And for series combination, this kind of formula is useful, but this is just opposite, right? So yes, you can remember like that, na? Right? So now next I'm going to discuss from where this formula is coming, right? So we are going to prove this formula, okay? Okay, so first I will discuss series combination, I will write this formula, and then I will discuss parallel combination, I will write this formula, right? Okay, finish, right? Done. So now I'm going to rub it. Okay, so first I'm going to discuss series combination, right? Series combination, right? Series combination. Okay, so now I'm going to draw a circuit of series combination of capacitor. Okay, so suppose three resistors are connected in series, right? And this combination is connected through a battery of potential B, right? Okay, so due to this, charge appear on the capacitor, right? So this is your positive terminal, right? So charge start moving, positive charge will appear, plus Q on this plate, minus Q will appear. Similarly on this plate, plus Q charges appear on this plate, minus Q charges appear. So here again plus Q minus Q, right? So as you can see, now charges appear on a capacitor, right? Okay, suppose this capacitor is having capacitance C1, this capacitor is having capacitance C2, this capacitor is having capacitance C3, right? This is your series combination. In series combination, you can see charge on each capacitor is Q, right? So in series combination, charge on capacitor will be same, right? Okay, so and you can see here, this capacitor is having capacitance C1, right? This capacitor is having capacitance C2, C3, right? As capacitance is different, right? As capacitance is different, so we can write here as capacitance, as capacitance is as capacitance is different, as capacitor is different, so potential drop across each capacitor is different, okay, right? Across each capacitor is different, right? Now first I'm going to calculate potential drop across capacitor C1, right? Now potential drop across capacitor C1, right? And you know potential drop, you know this formula Q is equal to CV, right? What we are going to find? V we are going to find, right? So from here we can write Q by C is equal to V, right? Here we are going to calculate potential drop across capacitor C1, right? Suppose that is V1, right? And that way will be Q by C, and this is how much? C2, right? Similarly, we can write for capacitors 2, 3, right? Okay. Similarly, we can write potential drop across capacitors C2, right? C2 is V2, okay? And that V2 is how much? Q by, and V3 is potential drop across capacitor C3, and that value is this much, right? Now V1 is known, V2 is known, V3 is known, right? So total potential drop across the battery is potential drop across this one plus potential drop this one as well as potential drop across that one, right? See now here potential drop is how much? V1, right? Across this capacitor potential drop is how much? V2, okay? So only these are the potential drop across the circuit, right? So this one plus this one plus this one is equal to this one, right? So further we can write now V is equal to V1 plus V2 plus V3, right? Now this V1 is V2, V3, everything is non-plus, just we have to substitute the value. But what about this V, right? See, we are drawing an equivalent circuit like this. Suppose this is your C equivalent, right? Okay, so this is your C equivalent. So C equivalent is also connected to V, and this capacitor is also drawing charge Q, right? So this is known as your equivalent. This is having plus charge, this side is having minus Q and plus Q, right? So from here we can write V is equal to, from this one we can write V equals to Q by C equivalent, right? So V is equal to C equivalent, and now I'm going to substitute the value. So Q by C equivalent, and this is Q by C1, Q by C2, and Q by C3, right? So Q everywhere is Q, so we can take common Q and cancel it, okay? So after this, now I'm writing here, right? Now see, here we can write like this: C Q by Q equivalent. Q is everywhere, so we can take Q as a common. So inside the bracket I have 1 by C1 plus 1 by C2 plus 1 by C3, right? This Q cancels. What is the formula? 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is your formula to calculate equivalent capacitance in parallel combination. Okay, it's in series combination, sorry. Okay, so in series combination we have to write one point, okay? So no, charge on each capacitor is same. In parallel combination, charge on each capacitor is same, okay? So next I'm going to discuss parallel combination, okay? Oh sorry, this is series combination, sorry. In series combination, charge on each capacitor is same, right? So next I'm going to discuss parallel combination, okay? So just write it. In series combination, charge on each capacitor is same. So next one is parallel capacitor, okay? So suppose capacitor is connected like this. So this combination is known as parallel capacitor, right? Okay. Suppose this one is your C1, this is your C2, this is your C3, right? Tell me, all capacitor is connected through same battery, right? So potential drop across each capacitor is same, right? See now, this capacitor is connected across battery of potential B. C2 is also connected through battery of potential B. So all is connected through same battery, potential will be same. So in parallel combination, potential drop across each capacitor is same, right? So suppose this one is having charge Q1, this one is having charge Q2, this one is having charge Q3, right? Okay. And suppose this is C equivalent of these capacitance, right? C equivalent of these capacitance, we can write like this, okay? And suppose this one is having charge Q, okay? So further we can write, you can see here, potential is same, right? But capacitance of each capacitor is different, right? So charge on each capacitor will be different, right? Capacitance is different. Now you know Q is equal to CV. This value is same, but this value is different, right? So Q will be different. So Q1 will be C1 into B. Okay. So we can write next step as capacitor are different, right? As capacitor is different. Charge on each capacitor is different, okay? Now first I'm going to write charge on capacitor 1, charge on capacitor C1, right? Charge on capacitor C1 is how much? Q1, right? And this Q1 is what? C1 into B. Similarly we can write, charge on capacitor 2 is Q2, right? And that Q2 is C2 into B. And Q3 is C3, right? So these are the charge on the capacitor, right? Okay, and this summation of this charge is equal to this one, okay? So in next step we can write this Q, right? This Q will be equal to Q1 plus Q2 plus Q3, right? Now, okay, so Q1 is known, Q2 is known, Q3 is known, Q is known to us, right? So by substituting the value there, we are able to find final expression, okay? So after this, I'm writing here, okay? So in place of this Q, we can write V C equivalent into B, right? Here C1 into B plus C2 into B plus C3 into B. You can see B is present everywhere, right? So we can take V as a common. So we taken V as a common, okay? So we have C1 plus C2 plus C3, right? This B cancels, so C equivalent is equal to C1 plus C2 plus C3. Okay, so you can see here Just I substituted the value of Q1, right? Value of Q is how much? From here. Q is how much? C equivalent into B, right? Similarly, Q1 is C1 into B. Okay, so we can write like this. Okay, so from here I got Q, right? This Q is how much? B into C equivalent into B, right? So from this figure, I got this relation, right? And just I substitute the value here, okay, in this one. So finally, I got this expression. So I took B as a common, right? So this B cancel. So finally, this one is coming, right? So this is for parallel combination, right? So if capacitor is connected in parallel, then using this formula, you are able to get equivalent capacitor, right? Equivalent capacitor is a single capacitor which stores same amount of charge as stored by combination, right? Okay. So I hope you written this part. Right now we have to write note. Okay. So you can see the potential drop each capacitor is same, right? So write note. Okay. In parallel combination, potential drop across each capacitor is same. Okay, so in parallel combination, potential drop across each capacitor is same, right? So this is all about for today's lecture. Okay.